and then the fiber is made to contact metal or ceramic pins at a known wrap angle to determine the coefficient of friction using data streams from input and output tension, which correspond to T1 and T2 values, where the T1 values, the pretension values, are shown in red over here. So since the standard operating procedure was used throughout the study, the raw data for the study consists of very typical looking diagrams, and it's typical to have high frequency and significant pretension variations throughout any given test for fiber to metal, fiber to ceramic test. So pretension variations have been the center of a lot of work that has already gone on in Goulston, and there are many reasons for that, and one of them is because the causes of pretension variation cannot be controlled, and that is shown in this diagram over here, because contact with pins and tension variations at the time of winding will cause pretension variations. And so precisely how winding tension variations at the time of winding can cause pretension variations is not known, but we do believe that because of the elastic nature of the spandex fibers, that they will store any tension variations at the time of winding, and that might cause pretension variations at the time of testing. So that means that if we implement a costly and time-consuming design change of the instrument with the aim of reducing the pretension variations, then we will still have these factors contributing to pretension variations and therefore undermining the project. So that's one reason why pretension variations have been central to any work that's gone on fiber testing. Another reason why we focus on pretension variations is because they are capable of causing imprecision in the reported coefficient of friction. And that isn't the case for hard yarn fibers because of this study in 1998, which states that the ratio of pretension to output tension, or the coefficient of friction, is constant for a wide range of pretensions. However, no such study has been done for spandex, and so there is reason to believe that pretension variations can result in imprecision in the reported coefficient of friction. However, today's study is going to focus on how pretension variation cause us to over-report the standard deviation in the coefficient of friction, or how pretension variations can cause an artificial inaccuracy in the coefficient of friction. So presently we use this study from 1998 as well to be able to make sure that pretension variations don't cause artificial inaccuracy in coefficient of friction. And that's because this study states that the machine compensates for variations in pretension by calculating the coefficient of friction at each data point. So let's see how that looks like. On the top left, we see the T1 and T2 data streams over the course of 1 second. And so according to the previous study, we go ahead and calculate the coefficient of friction at each given point, resulting in the top right image. However, when we shift T2 to the left, which would be equivalent to assuming that there is equilibration time between T1 and a subsequent change in T2, then the standard deviation seems to go down. So in this study, we aim to exploit this supposed decrease in standard deviation as a function of whether or not we skew T2 to the left or to the right, to be able to determine if there is an equilibration time, to determine what that equilibration time is so we can correct for it, and to determine how much standard deviation are we overestimating presently. So in the previous slide, we looked at 1 second of data for a fiber to metal test. Over here, we look at 30 seconds of data for a fiber to metal test, and we see that there is a peak at n equals 2, which corresponds to the lowest standard deviation is achieved at n equals 2, and keep in mind that n is the number of rows that T2 is moved up in relation to time in T1. And so the more the n, the larger T2 is shifted to the left in the previous diagram. And negative n values correspond to a shift of T2 below T1 and time. So over here we see that the data resembles a single peak system really well, but that system has a peak that is not centered at n equals 0, and that there is this artificial peak at n equals -4. So what happens when we look at 60 fiber to metal, fiber to ceramic data? We see that the second peak disappears, suggesting that what we were seeing there was actually a single peak system with random noise. And another thing that happens is that the peak at n equals 2 becomes prominent and is at 4%, and is maximum at 4%. So we can conclude based on this that over the course of large enough data set, we are overestimating the standard deviation and coefficient of friction by 4%, and that can be reduced by choosing n equals 2 to account for an equilibration time of 67 milliseconds between T1 and T2. The final way of looking at this study is to think of it as a method development. And the method here is that you have an instrumentation system with multiple data streams, and you can find the equilibration time as long as those multiple data streams are related to each other by a physical constant. So another example of an instrument that fits those parameters is the hard yarn friction meter, where the data streams are T1 and T2 as well, and the constant that relates them is the coefficient of friction. So we plot the standard deviation and coefficient of friction as compared to n like we had in the past, and we notice that there is a pronounced peak at n equals 3 to n equals 5, and that corresponds to a decrease in an overestimation of standard deviation and coefficient friction of about 20 to 30%. So with that, we come to